Imagine if the most significant image ever captured in human history didn't originate from the James Webb Space Telescope, the Hubble, or even from Perseverance on Mars, but instead from a spacecraft launched over 4 decades ago. Voyager. One now more than 14 billion miles from Earth, has returned an entirely unexpected photograph from the outermost reaches of our solar system. The image comes not from one of today's high-tech instruments, but from a spacecraft launched in 1977, one thought to be long past its imaging prime. And yet this single frame is captivating scientists and astronomers worldwide, triggering debates and fresh theories at the very frontier of known space. This surprising image was taken by Voyager 1's Imaging Science subsystem, a system of narrow-angle and wide-angle cameras that were never designed for deep space astrophotography at such an immense distance. In March 2025, NASA's Jet Propulsion Laboratory quietly released a new image captured as Voyager passed through the heliopause, the boundary where the sun's solar wind gives way to interstellar space. At first glance, the image seemed to show nothing more than static, scattered green and purple pixels against a black backdrop. But using new machine learning algorithms trained on data from missions like Cassini at Saturn and New Horizons at Pluto, scientists were able to denoise and reconstruct the image. What emerged stunned them: a vast filament-like structure spanning the frame, resembling glowing strands of plasma stretching through the dimming solar boundary. This wasn't just another pale blue dot. It was something entirely different, an immense luminous network that appeared to trace invisible magnetic field lines or possibly interstellar dust flows entering our solar system. Notably, when Voyager 1 last captured this region in 2012, nothing like this was visible. What's more, the image's brightness fluctuations directly correlated with irregular plasma wave activity and cosmic ray flux detected by the spacecraft's instruments. This suggested that what we're seeing isn't static. It's a snapshot of dynamic interactions occurring at the intersection of our solar system and the vast interstellar medium. Voyager 1's journey began in 1977, initially tasked with exploring the outer planets. It far exceeded expectations, delivering critical data from Titan, Saturn, Uranus, and Neptune. After passing beyond Neptune, it continued its path toward the edge of the Sun's influence and officially entered interstellar space in August 2012. Since then, Voyager's scientific payload, including its plasma detectors, magnetometer, and cosmic ray sensors, has remained active even as its cameras were largely dormant to conserve power. Recently, NASA engineers managed to update its flight software, reawakening its imaging system for one final ultra-long exposure. The resulting image, created from over a dozen exposures of up to 4 hours each, was stitched together using custom algorithms developed at JPL. The result was not only a technical triumph, but a visual revelation. It provided the first optical glimpse of the heliopause, a region long considered invisible to traditional photography. The implications are vast. Scientists are now attempting to interpret what the image shows. 3 leading hypotheses have emerged. Plasma physicist Dr. Leila Moreno of the University of Chicago suggests the structures may be filamentary plasma formations caused by the Sun's magnetic field lines interweaving with the interstellar magnetic field. Charged particles traveling along these lines might emit the faint glow seen in the image. A second theory, led by Dr. Caspar Vogel at Cornell, proposes that interstellar dust grains, electrically charged as they cross into the heliopause, are colliding with solar wind particles, producing faint light only visible through long-duration imaging. The most speculative theory comes from theoretical astrophysicist Dr. Amara Owe of Ghana. She posits that the image might be showing evidence of axion-like dark matter particles converting into photons under the influence of strong magnetic fields, a process the heliopause may naturally support. This would make Voyager 1's image a rare, possibly groundbreaking piece of indirect evidence for dark matter. Although these ideas remain speculative, all 3 are grounded in sound physics and supported by Voyager's onboard measurements. Already, peer-reviewed papers are appearing in major journals like Nature Astronomy and Physical Review Letters, attesting to the seriousness with which the scientific community is treating this discovery. Yet what truly deepens the mystery is what researchers found next. Analysts at JPL uncovered a faint but statistically significant hexagonal pattern embedded within the plasma filaments. This honeycomb-like lattice isn't merely visual noise, the hexagon's alignment with Voyager's spin axis, and not with known magnetic geometries, suggests it may be either a data artifact or, more intriguingly, a real spatial structure formed by alternating magnetic domains. Could these be magnetic reconnection islands? Or are we seeing a type of plasma instability never before documented? The concept of a giant hexagonal pattern at the heliopause is unprecedented. While hexagonal structures have been observed, like the one at Saturn's North Pole, nothing of this scale or in this region has ever been proposed. This anomaly is puzzling scientists and fueling late-night discussions in labs and observatories around the world. But the story doesn't end there. Just days after NASA released Voyager's denoised image, a team from ESA, experts in low-light imaging from the New Horizons mission, ran the raw data through their advanced quantum-assisted enhancement tools. What emerged was even more startling. A second filament, broader and fainter than the first, tilted exactly 60 degrees in relation. This wasn't an error or lens artifact. It was a real structure. When the ESA team overlaid both filaments in a 3D model of Voyager's field of view, they noticed a striking symmetry. 12 radial lines emerged from the pattern, arranged like spokes on a wheel. One set was bright and narrow, the other wide and ghostly, layered like harmonics in a sound wave. The whole structure rotated across the image field like the dial of a cosmic clock. The angular precision was too consistent to dismiss as coincidence. ESA scientists hypothesized that this might be evidence of a magneto-hydrodynamic resonance, an oscillation at the boundary between solar and interstellar plasma. One physicist remarked that it's as if the edge of our solar system has its own heartbeat, and we've just begun to hear it. None of our existing models predicted anything like this. The Parker spiral, outer heliosheath simulations, and even Voyager's particle pressure trajectory forecasts failed to anticipate the structure's presence. This discovery suggests that the solar boundary region may be much more complex, perhaps even layered in a higher dimensional structure than previously imagined. For planetary science and astrophysics, this represents a monumental turning point. We now have direct visual evidence of processes occurring where the sun's influence wanes and the galaxy begins. These aren't just data points. They're visual records of large-scale plasma and magnetic field interactions, possibly revealing new physics beyond the standard model. For the public, Voyager's image reawakens something deeply human: wonder. In an age of distraction and division, this quiet, ancient spacecraft has offered a gift, a deeper perspective. Voyager was launched when disco was popular and computers filled rooms. It has 68 kilobytes of memory and transmits at 23 watts, less power than a nightlight. And yet it continues to teach us about the cosmos. What this image represents goes beyond visual beauty. It's a reminder that exploration isn't always about fast rockets or shiny new satellites. Sometimes the biggest revelations come from old data reanalyzed with new tools, from the patience to look again, and from the willingness to question what we thought we understood. The Voyager mission reminds us that our solar system doesn't merely end. It transitions, it interacts, it vibrates, and now we know it may even echo through plasma filaments, hexagonal patterns, and the spokes of a vast magnetic wheel. If such structures exist here, could they exist elsewhere too? Could every star system have its own echo, its own boundary pattern, its own heartbeat? More provocatively, might these structures encode information, not in the sense of alien messages, but in the rhythms and geometries that point to deeper physical laws? The universe, after all, is not only energy and matter, it is also information. And perhaps through Voyager's faint signal, we are beginning to receive our first whisper of that deeper truth. Voyager 1 is not merely a relic, it is a messenger. Its new image from the very edge of our solar system has upended assumptions and reignited curiosity across the sciences. It reminds us that exploration doesn't stop, it evolves. And sometimes, from the farthest places, the faintest signals carry the most profound messages.